Alright, home stretch. This is our last chapter of the course. It's on rotational dynamics. So basically you can think of this as pretty much everything we've done for linear motion, for translational motion. We have to translate all of what an object does and how it moves, how it behaves for an object that's rotating. Now we've done that in some degree within chapter 7, right? Chapter 7 we started with circular motion. We had like a point particle, right, or a mass like swinging on a string or going around a track or something like that. So it was an object at the end at the end of some radius vector moving around in a circle. Now we're going to take solid objects and we're going to rotate them, right? Think about like a sphere, right? So you're rotating a sphere or you're rotating a solid disk. So these objects have mass, but they also have some shape. So we're going to talk about how that affects their motion. So we're basically redefining Newton's laws for a solid object, a massive, dense object that rotates under some applied force. So in order to do that, we have to define a new type of product between two vectors. We already dealt with the dot product when we were talking about work, and that resulted in a scalar. So for those of us who haven't seen this level of vector calculus, just do a quick review or a quick introduction to the vector product. Right, so I have two vectors, A and B. Right, we used to multiply them by AB cosine theta, and then we got a scalar, right, and that's what we use for like work and energy concepts. But there's a new type of product that actually results in a vector. Right, we call this the cross product because our notation we use an X instead of a dot. Right, so we have the cross product from back in chapter 5. Now we've got the cross product. Right, so the cross product results in a vector A cross B that's always perpendicular to the plane on which A and B lie. Right, so let's say this was like the XY plane. Right, let's say you had two vectors. You had one in the X direction, one in like the X and Y direction, but they're both lying on the XY plane. This vector would be in what we call the Z direction, right? Because in real life, everything, we live in 3D space. Up to this point, we've only dealt with motion in 2 dimensions, right? But we have to define this third this third degree, right? This third axis, the Z-axis, to represent the third dimension. Okay, so A cross B is defined mathematically by the magnitude of A times the magnitude of B times the sine of the angle between them. Right. So it's different from the dot product because let's say A and B were pointing in the same direction. Right. If I had A and B both pointing in the same direction, the angle between them would be 0, and so the cross product between those two vectors would be 0. Okay, so we'll talk about that a little more when we talk about the XY Z axis and what effect that has. Okay, so if we have two vectors in the same direction, the angle between them 0, sine of 0 is 0, so the cross product would result in a 0 vector. Right, there actually wouldn't be a vector perpendicular to them. So let's talk about the practical use of this on our XY plane. Right, if you're looking at the screen right now, the surface of the screen is my XY plane, right? But coming out towards you is actually the Z-axis, right? So that's our representation of 3D space. So we've got a new axis. The positive Z-axis is coming out towards you. Right, the negative Z-axis is going into the screen right now. Right, it's going into the screen or into the page if you're looking at a piece of paper. So the cross product between X and Y is the Z vector. Right, So if these are my 3 unit vectors, right? X hat, Y hat. The cross product between X and Y is Z. It's coming out towards you. Okay. So how do I know it's coming out towards me and it's not going into the page? We find the direction by using the right hand rule, and I'll post a video, a separate video on how to use the right hand rule, because it's kind of hard for me to explain without telling you. But if you took your right hand and you point your fingers in the direction, right? Take your right hand, make sure it's flat. You point your fingers in the X direction, and then you want to curl your fingers in the direction of the y-axis. Right, so I'll be curling my fingers up towards the y-axis. My thumb is pointing towards me right now. Okay, so if my fingers are in the direction of the x-axis, flat, I curl them in the direction of the y-axis. My thumb is pointing in the direction of the z-axis. So that would be the direction of the cross product of those 2 vectors, one pointing in the x direction, one pointing in the z direction. The cross product is not commutative. What does that mean? X cross y is not equal to y cross x. So if I did the same right hand rule, but I pointed my fingers in the direction of y, up in the air, right? So my right hand is pointing in the positive y direction. My hand is flat. And if I curl them to the right in the direction of the x-axis, my thumb is now pointing away from me, and it's pointing towards the screen. So my thumb is pointing in the negative z direction. So what I'd like you to do, if you want to pause the video, do the cross product for the remaining 4 using the right hand rule to verify that the right hand rule gives us the direction of the resultant vector. Okay, so do y cross z, z cross x, and then do z cross y and x cross z. Okay, so practice using the right hand rule for all 6 of these. Okay, and verify, when you use the right hand rule, verify that your thumb is pointing in the direction of the resultant vector. Okay, so why do we need the cross product? We need the cross product because we have to define a new action that rotates an object. Okay, up until this point you see this should look familiar, right? If you're applying a force on an object, you know it's a vector and it'll cause some sort of acceleration, right? Chapters 1 through 5, or technically 4, 5 was energy, but chapters 1 through 5, if we were dealing with a force, it was pointing in the x and or the y direction, right? Some combination of the two. But it resulted in the linear motion of some object. Then when we got to chapter 6, there was a force on an object that was going around in a circle, right? So there may have been a force causing it to rotate like this, giving it some angular acceleration, but there was a force pointing towards the center that was keeping it on that circular path, right? So we had a centripetal force causing a centripetal acceleration, but then at the same time we may have had some tangential force that was causing it to accelerate in the clockwise or counterclockwise direction, right? So you had 2 different types of angular acceleration. The rest of this chapter we're going to be dealing with an object's angular acceleration only, because now we're dealing with a solid object, right? So the solid object is just going to rotate around an axis. There's not a centripetal force keeping some point particle on a circular path. It's just a solid object like a wrench, right? Or you can picture this as like a door on a hinge, right? This would be its hinge and this would be the door. So this would be a force you applied to close that door, right? To close a door or open the door, or in this case, like tighten or loosen this bolt using this wrench. So we want to rotate this solid object. We want to, let's say we want to loosen this bolt, right? We want to loosen this bolt, so we're going to apply a force, and I'm going to turn the wrench lefty-loosey, right? Lefty-loosey, righty-tighty. So it's going counterclockwise. I expect this bolt to be loosened. But this force is causing this to rotate. So this force is not necessarily applying strictly a linear or causing a tangential or a linear acceleration. it's causing an angular acceleration. Okay, it's causing an angular acceleration. Now, if you were trying to open or close a door, if you applied a force closer to the hinge, it would be more difficult to close that door or open that door. So we want to be a certain distance away from the hinge, right, or this bolt, to make it easier to rotate, right? So we want to apply a force farther away to make it easier to rotate this object. So what that means is this distance right here, this R, sometimes you'll see it referred to as the lever arm in some textbooks. This distance R, that's a vector, right? It's a vector pointing from this pivot point, or this axis of rotation, to where the force is being applied. Okay, so this value R, okay, I'll often refer to it as just a radius vector, right? It points from here to where the force is being applied. That's my R vector. Okay, so we know from experience, opening and closing doors, the bigger this number is, the easier it is to close the door. Same thing with this wrench, right? If I held it up here, it's going to be much easier to loosen or tighten this bolt. Also, the stronger force I apply, the easier it's going to be to rotate this object. So we have a new property that's dependent upon this value R and this value F. We call that torque. And torque is the cross product between these two vectors. It's the cross product between these two vectors. Now if we go back up here to the cross product, it depends upon this angle theta. So we're going to talk about how theta, or in this diagram it's alpha, but we're going to talk about how the angle between these two vectors affects the torque. Okay. Now what's the angle? We got to be careful here, because a lot of our web assigns, they give you funny angles and you have to kind of interpret it. Okay. The angle between these two vectors, okay, the angle between the R vector and the F vector, is actually this angle right here. See this angle right here, phi? If you drew an arrow for R and you moved it and you put the tails of R and F together, right? So now your R vector is right here. Okay, the tails of the two vectors have to be connected to apply the cross product. Okay, so take your R vector, move it up here. This angle phi is the angle between the R vector and the F vector. R vector, F vector. Okay, so be careful, make sure you're using the right angles when you're like calculating torques for like WebAssign and stuff like that. So the definition of torque is the cross product between the radius vector and the force vector. So it's dependent upon R. Okay, the farther away I am from the pivot point, the larger the torque. Depends on the force that I'm applying. The larger the force, the larger the torque. And it depends upon the angle between the two vectors. Okay, angle between the two vectors. So let's take a couple cases, right? A couple like common angles here, and see how it affects the torque. I'll do that on the next slide. I've got a couple different scenarios there. So it's tau, right? It's a lowercase tau. That's the symbol for torque, and its units are Newton meters, right? Now, which is kind of weird because they're the same units as energy, right? But again, torque is a vector. Okay, so we don't call this joules or anything. We just call it Newton meters. We don't have a special SI unit for torque. Okay. So again, it depends on how far away you are from the pivot point, how strong the force is, and the angle at which you're applying the force relative to that radius vector or that lever arm. Okay. So let's talk about a couple scenarios, right? So these red arrows are all like different force vectors. Okay, they're different force vectors. Notice that the radius vector doesn't change for this object. It's always going to be pointing in this direction. All right. So let's take the scenario where we're pulling the wrench in the same direction as the radius vector. The angle between the R vector and F vector in this case is 0. Sine of 0 is 0. Okay, so you're exerting no torque if you're pulling in this direction. Let's take that force and switch its direction. if I push directly into the wrench, or if I push along the edge of the door towards the hinge, the same thing is going to happen. The angle between the radius vector and the force vector is now 180. The sine of 180 is 0. Okay, so in both of these cases I'm not going to exert a torque because the force is in the same direction as the radius vector. How do I maximize my torque? I maximize my torque by applying the force perpendicular to the radius vector. Alright. Now if the force vector is perpendicular to the radius vector, the angle between them is 90. Sine of 90 is 1. So the torque would just be R cross F. Right? So that's how we maximize our torque. We apply the force perpendicular to the radius arm. So sine of 90 is positive 1. So I'd have a maximum torque counterclockwise. Right? Maximum positive torque. If I switch the opposite direction, so I can do this kind of two ways. I can say the angle between the radius vector and my new force vector, it's either 270 degrees, right? Because I got to go all the way around first, second, third quadrant, 270 degrees. Or I can go in the opposite direction and say the angle between the two vectors is negative 90 degrees. In both cases, the sine of 270 and the sine of negative 90, my calculator is going to tell me that's negative 1. So I'm still maximizing my torque, but I'm maximizing it in the negative direction, in the clockwise direction. Okay, so I'll still have a max torque, I'm just changing the direction. Okay, still R cross F, R cross F. You just have to make sure which one is positive and which one is negative. And what will happen is we'll switch our coordinate system around to kind of make our lives easier, where if clockwise is positive and that makes my life easier, I'm going to do that. And I tend to do that fairly often, so we'll see when that makes our situation easier. Any of these vectors in between, right, this right here, let's say it's 45 or 30 degrees or 60 degrees or something like that, any angle between 0 and 90, you're going to have a fraction of your max torque, right? Put like the sine of 45 in your calculator, you get root 2 over 2, right, which is a little less than 1. Put the sine of 30, sine of 60, right, all those values are in between 0 and 1, so you're not going to have max torque because some of your force is being applied parallel to the radius vector. Alright, so these are the scenarios we're going to be dealing with. Right, forces that don't apply a torque because they're parallel to the radius vector, and then forces that are making some angle with the radius vector generating a torque. Okay, so again, that's why it's very important to be able to determine what this angle is between your radius vector and your force vector. So we'll do a pretty basic scenario here. We have some options in problems similar to this, and we'll see when we get to like static equilibrium. There's always a convenient axis of rotation to pick that helps us make our problem easier to solve. But our first rule is if we have an object, right? This is a steel beam. Okay, so we'll model it as like a rectangular prism, right? A steel rectangular prism. So it's solid, it's got a mass, and it's being supported by a fulcrum. Okay, so you can kind of picture it as like a seesaw, but that's like off balance a little bit. Right, so we've got this little this foundation right here, and it's supporting the steel beam. But at the same time, we have to remember this for all of our solid objects. At the same time, this object is experiencing the force due to gravity at its center of mass. Now in this course, the center of mass for every object is going to be the center of that object. Right? Every object is going to have a uniform mass distribution, you know, like one side's not going to be heavier than the other. So for all of our objects, the force of gravity is going to be applied right in the center of the object. So in this problem we have a mass. We know how long the beam is. We know the beam is 4 meters long. And we know how far from the right side the fulcrum is applying its force. And so there's a there's a supporting force, right? There's a contact force that the fulcrum is applying on the beam, and that's 1.2 meters from the right side. So we're looking for the torque that's applied by the force of gravity, right? If I were to let this system go, it's going to rotate like this. This side's going to fall down, this side's going to ascend like this, and the whole thing's going to rotate counterclockwise, okay, mainly due to this gravitational force. Okay, so since the gravitational force is going to cause this thing to rotate, gravity is applying a torque. So the first thing I want to do is I want to pick a spot, right? I want to pick a spot that's going to make it the easiest. It's going to make it as easy as possible to solve for this torque due to gravity. And what I'm going to do, and you'll get better at this with practice. What I'm going to do is I'm going to pick this point right here. And the reason I'm going to pick this point right here, okay, I'm going to pick this spot right here. That means the radius vector for the applied force from the fulcrum is 0. Okay, so any force that's being applied right at the object's pivot point or the axis rotation is 0, right? Because torque is RF sine theta. If R is 0, torque is 0. So I'm going to pick this point right here to be my axis of rotation, so I don't even have to consider the torque being applied by this fulcrum. All I have to do is worry about the torque applied by gravity. Okay, so here's my picture. Alright, the reason I picked this is because I'm eliminating that force. Right? That force is not going to apply a torque. Alright, so it's still applying a force on this object, but if I pick this to be my pivot point, it's not generating a torque. Okay, so right here R is 0. The only other force generating a torque is the gravitational force. Okay, and we see if we let go of this thing, it's going to fall and it's going to rotate counterclockwise. So the net torque is only due to gravity. So it's going to be the cross product between the gravity vector's R vector, okay, this right here. So I'm drawing an arrow from R equals 0 to where the gravitational force is being applied. So it's cross product between that vector and that vector. Okay, that vector, that vector. So it's R cross F sub g, which is R Fg sine theta. Now the angle between these is 90. Okay, now you're looking at this and you're saying, well, you know, if I went counterclockwise, it might be negative 90. Don't forget that we're taking this R vector and we're moving it so that its tip, or that its tail, is right here and its tip is over here. Okay, so we got to connect the tails of the two vectors, R cross F, and the angle between them is 90 degrees. So R cross F, this is a great opportunity to practice the right hand rule. R cross F, the torque vector should be out towards you. Okay, and that's the positive z direction. R cross F, that's out towards you. Okay, so this goes to 1, which is good. I like that. Okay, 90 degrees, sine theta goes to 1, so it's just the product of the radius vector and the gravity vector. And the gravity is mass times acceleration due to gravity. I get the mass, I have the length of the R vector, these are just magnitudes now, and I get the torque applied on this steel beam. Okay, the more massive it is, the greater the applied force, so the greater the applied torque due to gravity. Okay, again, this is a simple case. You've got one torque. I picked a convenient axis to get rid of this one, right? I always want to pick a pivot point where some force is being applied if I don't have to solve for that force. Right? They didn't ask me to solve for this applied force, so that was nice. It got rid of this applied force vector. I didn't have to answer anything about it. So watch out for your WebAssign. You know, you'll have gravity, and maybe you'll have like a tension, and you know, maybe the tension will be acting in a direction that's not perpendicular to its radius vector. Okay, so this won't always be 90, and then you may have more than one torque. All right, so we do the same process, apply the cross product, and just like Newton's second law, we'd add up the torques. Right? We'd have a net torque. Maybe they'd ask for the net torque, and then the individual torque due to some force. Okay, so we've got this definition of torque, right? RF. We've got the cross product between two vectors, but torque is also a scalar. Right? Torque is also a scalar. And we see that if we apply a torque, we're going to cause something to speed up in either the counterclockwise or the clockwise direction. Right? If we apply a force, we accelerate an object. So we're applying a force here, right? We've got this torque, but it's dependent upon this force. So we're applying a force, we've got to be accelerating this thing somehow, right? If there's a net force on something, it's got to be accelerating. But since we're applying a torque now, we're causing it to accelerate in the clockwise or the counterclockwise direction, so that's an angular acceleration. Okay, that's an angular acceleration. So this is Newton's second law for rotational motion. Okay, alpha takes place of A, tau takes place of F. Right? But it's not just dependent upon the mass of the object. It's dependent upon some other property of the object. It's not just how massive it is. Okay, so there's a new type of inertia that we have to define for these solid, dense, massive objects that we're trying to rotate. Because it's not just a point particle anymore, right? It's not just a block on the end of a string or a car going down a road. It's an object that has a bunch of little tiny sections of mass in it, right? Technically we need calculus for this next slide, but we'll forego that. This is algebra based. But that object has little tiny masses all through it. Okay, it's not a point particle anymore. It's got geometry, it's got a volume, it's got density, all that stuff. Okay, so this we use I. Okay, not to be confused with impulse a while back. We always have an overlap with variables, which can be annoying, but this is a new I. All right, so this is a rotational inertia of an object. Okay, so it depends upon a lot of things. Sometimes it'll be referred to as the moment of inertia. So when I say rotational inertia, I also mean the moment of inertia. And so it doesn't just depend upon the mass of the object, it depends upon its geometry, it depends upon its shape. Right? How is the mass distributed across this object? And you're looking at this table, it's got a lot of formulas, right? It's very overwhelming. You'll always have access to these, so I'm not asking you to memorize these. But these expressions here came from calculus, right? We actually had to integrate over the volume of this object, of these objects, to get their new moments of inertia. All right. So if you're asked for if you need to use the moment of inertia for, say, a cylinder or a disc, and most commonly you'll see cylinders and discs, you'll see like solid spheres, and you'll see these two cases of a thin rod. Right. We just did like a steel beam, like this. Right. Its axis of rotation is different, and for different axes of rotation we get different moments of inertia. Okay, so these are the two that we'll deal with. Okay, if you have a different axis somewhere, you got to use calculus to find it, and we're not going to bother with that in this course. So we've got these two cases for like a thin beam, right, like a rectangular prism. We've got a disc and we've got a solid sphere. Those are our most common. Okay. WebAssign might give you one with like a cylindrical hoop. Take your time, go look up the expression for the moment of inertia and use that. And so what I'm going to do is when I need a moment of inertia, I'm going to plug it in, but I'm going to plug the variables in first. Okay, and there's an advantage to that in this section. Rather than calculate the moment of inertia, let's say I have the mass and the radius of some disk. Rather than calculate that, I'm going to plug the variables in, and we'll see why that actually helps us. Okay. So we have, for translational dynamics, right? Newton's second law originally, we had a force, we had a mass, we had an acceleration, right? And Newton's second law gave us the relationship between those three properties. Now that we're rotating something, our force is now a torque. Our linear, or our translational acceleration, is now our angular acceleration. And our mass, our object, the acceleration of the object doesn't just depend on the mass, it depends on the rotational inertia. Okay, depends on all these properties of the object, right? The mass and how that mass is distributed amongst the shape of the object. Okay, so we'll do a couple Newton's second law problems that deal with applying a torque on an object. Now both of these objects are cylindrical disks. So for a cylinder or a disk, we're going to use 1/2 mr squared for the moment of inertia for the object. Okay, cylinder or disk has the same expression for the moment of inertia. So this first one, we've got a steel cylindrical wheel. So I'm going to model it like a cylinder or a disk. It's got a mass of 15 kilograms and a diameter of 0.5 meters. Now, you know, those problems on like the SAT, they like to sneak in diameter when you're supposed to have the radius and stuff, trying to trip you up. This is one of those cases, okay? So we're giving you the diameter. Make sure you divide that by 2 before you like plug in the radius. So it starts from rest and it reaches 8 revolutions per second in 15 seconds. So that tells me this sentence right here, or this first part of the sentence says, I've got an initial omega, I've got a final omega in revolutions per second, so I gotta, you know, convert that to radians per second. Then I've got a time interval. So I've got a change in angular velocity over a time interval. I can find the angular acceleration. Right, so this phrase right here is going to give me the angular acceleration. We want the force applied tangentially to the edge of the wheel. Okay, so there's got to be something, right, that's applying a force on the edge of that wheel that's causing it to rotate. So I'm looking for that tangential force. If I need to find that force, I'm going to have to find the torque first. Okay, and this will be a pretty common setup for these types of problems. So here's my, you know, it's not really a free body diagram, but it's still a diagram of the rigid object. I'd like to put some vectors reminding me of the direction of the object's rotation. So there is some force being applied somewhere on this wheel tangentially. Okay, so maybe you're grabbing the side of the wheel with your hand and you're turning it, right? So you're applying a force and you're rotating it, you're giving it some angular acceleration, and then some time later it's going to have some angular velocity. So the first thing I'm going to do is I'm going to take my Newton's second law for rotational motion. Tau equals I times alpha. Okay, so notice how it looks a lot like F equals ma. F equals ma. Now for the cylinder, the moment of inertia is 1/2 mr squared. I've got two expressions now for torque. I've got Newton's second law for torque, and then I've got the cross product definition. Now what I'm going to do here is I'm going to pick this point, right? There's some force being applied tangentially to it, right? So I'm going to pick this spot right here, according to my diagram. So this is the force vector. The radius vector that meets where that force is being applied is this right here. Okay. So in this case, the r vector and the f vector are both perpendicular to one another. So the angle between them is 90. Once again, that's very nice. Sine of 90 is 1. And so tau is just the radius vector times the force vector. Now we'll see this happens quite often, right, in these types of problems, torque problems. I've got I alpha and I've got RF. Both of those are equivalent expressions to force. So in a lot of scenarios, we're just setting these two expressions equal to each other. I alpha equals RF. Right? In this case, there's only one force applying a torque, right, which is good, so we don't have to worry about like adding up torques or anything like that. So I set I alpha equal to RF. I'm looking for this tangential force. Notice I haven't plugged anything yet because I want a nice expression for my force first. So I'm going to divide both sides by R, F is equal to I alpha divided by R. Now, I'd like to substitute my expression in for my moment of inertia, 1/2 mr squared. So it's 1/2 mr squared times alpha over R. 1r goes away. So here's my expression for my force. I know the mass of the wheel. I know the radius of the wheel. I need alpha. So that's why we were given all these rotational kinematics quantities, right? The change in angular velocity and the time. I'm going to use these to calculate alpha, so that way I can determine the tangential force. So I'm going to use omega final is omega initial plus alpha t. Solve this for alpha. Substitute. I converted 8 revolutions per second to 16 pi radians per second. All I had to do was multiply it by 2 pi. So I got 16 pi radians per second over 15 seconds. What's 16 pi over 15? I don't know. I don't care. Right? That's correct. Right? It doesn't have to be plugged in a calculator. No big deal. I'll just bring it along with me. I'm not a big fan of fractions, but maybe, you know, down the road something will cancel out, right? So it's no problem for me to just keep writing 16 pi over 15 for the angular acceleration. So now that I have this, I can plug everything in. The mass is 15 kilograms. The force, or the radius, is 0.25 meters. Also 1/4 of a meter, right? Those nice decimals, I can, you know, switch those to fractions. Then I've got the angular acceleration, 16 pi over 15. That's why I kept it a fraction. It's kind of a made-up problem, you know. I like to make up problems with nice numbers. The 15s cancel out. I've got 16 pi divided by 4. There's also this 1/2 here, right? So I've got 1/2 times 1/4 times 16 pi. So I've got an 8 in the denominator. I've got a 16 over 8, which is 2. So 2 pi newtons. Kind of a weird, you know, like I said, the problem was made up to have nice numbers. So if you have pi in a force, it's okay, right? So it's 2 pi newtons, right? And again, a lot of cases we're setting, if we're looking for that force, or if we're given that force, we set RF equal to I alpha. Look up your moment of inertia expression for whatever your object is. Plug that in. You've got an equation, and you've got enough information to solve for one of those variables. Typical classical physics problem. Alright, second problem. We've got another disk. Okay, it's a solid cylinder. There's a mass of 2 kilograms. It's got a radius of 0.4 meters. Sometimes you'll be given that in centimeters, so watch out for that. You know, we'll be dealing with like small disks. Make sure you convert everything to meters. It's used to draw water from a well. So there's a bucket suspended by a string, and this wheel, we rotate it, okay, and then we lift the bucket. If we were to let go of the wheel, that bucket would accelerate in the negative y direction, and it would cause the reel, or the wheel, whatever this disc is, it would cause it to rotate. Okay, so there's a bucket. It also has a mass of 2 kilograms, and it's wrapped around the cylinder. So we're looking for the tension in that cord, and then the acceleration of the bucket. Okay, so basically we've wound the cable up. The bucket has been lifted, and then we're going to let go of the wheel, and then the bucket is going to fall. Right? So we're looking for the acceleration of the bucket, and then we're looking for the tension in the cable as it falls. And it says how far does it fall. So this looks like some kinematics, right? Falls from rest, falls for 3 seconds. We want to see how far it falls. Okay. So we need the acceleration of the bucket. Now what's happening here is the bucket is accelerating in the negative y direction. So it's got an A, right? Our old A from chapter 4. Right? It's accelerating in the negative y direction. It's not necessarily in free fall though. If I draw my free body diagram for the bucket, I've got gravity in the negative y direction, but there's also a tension in the positive y direction. Now we'll see that the numbers come out where it looks like it is in free fall, but that's just because I I picked nice numbers and everything just kind of went away. So, but this process is the same, and we can practice it with different masses. So I've got gravity in the negative y, I've got tension in the positive y. All right. So I use this, I draw my free body diagram so I can write Newton's second law for the bucket. Now, if you notice, I wrote the gravity is positive and the tension is negative. Okay. There should be a mass of a bucket right here. Sorry, that's a typo on my part. Okay, so I'll go back in there and fix it. That's mass of the bucket. Okay, so this is Newton's second law for the bucket. There's my free body diagram for the bucket. I chose down to be positive, right? I chose down to be positive for the bucket because as the bucket descends, then this is going to rotate clockwise. So this is one of those scenarios I was talking about. I'm basically, everything is going negative, but I'm calling that direction positive to get rid of any unnecessary negative signs. So this bucket descending is going to cause a clockwise rotation of the wheel. So this alpha is in this direction. I'm going to call that positive, so it matches this A, which is also positive. It's kind of like that, you know, one mass hanging, one mass sliding across a surface type thing. Okay. There's 1 degree of freedom. I just have to pick the most convenient direction to be positive. Alright, so Newton's second law for the wheel, there's a torque being applied on the wheel. That torque is equal to its moment of inertia times its angular acceleration. Okay. So the moment of inertia is again 1/2 mr squared times the angular acceleration. What is the force that's generating the torque? What's the force generating the torque? It's the tension. Okay, so the tension is pulling on this wheel and it's causing it to rotate clockwise. Okay, so it's T times R. Again, just like with the previous problem, the tension is being applied perpendicular to the radius vector. So sine of 90 is 1, and so I don't have to worry about sine theta. It's just the tension times the radius vector. So again, like with the last problem, I'm going to set I alpha equal to TR. So set this expression equal to this expression. Okay. So now I get an expression for the tension, right? T equals 1/2. This M right here is the mass of the disk. Notice I have two different objects. I've got the mass of the bucket and I've got the mass of the disk. Okay. So I'm giving this a subscript, M sub D, right? M sub D. So I've got an expression for the tension, but it's in terms of the angular acceleration. Right? They didn't say anything about the angular acceleration in this problem. Okay. So I got to figure out how to work with this angular acceleration, this unknown variable. Okay. So here's what I'm going to do. If you remember, there's a relationship between my linear velocity or my tangential velocity and my angular velocity. Okay, and omega is v tangential over r. So again, I'm going to do this little thing where I kind of cheat with mathematics a little bit. I'm going to multiply both sides by delta over delta t, right? If you're a calculus guru, you see that basically what I'm doing is I'm taking the first time derivative of both sides of the equation. All right. If you have no idea what I just said, don't worry about it. But this is basically like d over dt if you're a calculus person, right? So again, I'm kind of cheating, kind of informally showing you that if I take the rate of change of both sides with respect to time, the left side becomes alpha. The radius vector is constant, right? So I can pull that out, 1 over r, and then I have delta v over delta t. That's my tangential acceleration. Okay, that's a tangential. So just like omega is v tangential over r, alpha is a tangential over r. But here's a weird thing. This a tangential, right? Every spot on the edge of this disk has a tangential acceleration. Okay? If it's rotating, it's got an angular acceleration. It's got a tangential acceleration, right? A tangential, A tangential. But guess what? As this thing descends, it's got an acceleration. This bucket's acceleration is the same as the tangential acceleration of the disk. So this A is the same as this A right here. So anytime I see an alpha and I don't know anything about the angular acceleration and I'm not being asked to solve for it, I can substitute A over R. Now this is not the centripetal from last chapter. This is the tangential acceleration of some point on the edge of that disk. Okay. So what I'm going to do is I'm going to come back here to my tension and I'm going to substitute that in. So T is 1/2 the mass of the disk times its radius times the tangential acceleration divided by the radius. Okay, so 1r went away here, right? When I solved for the tension here, 1r went away. Okay, so I've got 1/2 mr times a over r. So now my second radius, right, this r term goes away. So now my tension is actually 1/2 the mass of the disk times the acceleration. Okay, so I have an expression for T. I haven't solved for it yet, but I've got an expression for T. So what I'm going to do is I'm going to pause this real quick and I'm going to upload an updated solution because I saw that this typo has some pretty significant consequences to what I'm doing solving here. So I'm going to pause this real quick. I'm going to upload this video because it's probably been a while anyway. So I'll upload an updated solution for this and I will continue the next video and solve this problem. Okay.